We've now got up to the work energy theorem. So we're halfway through what you're supposed to know about work energy and power. Now, when we look at the next bit, it's about conservative forces. If you want to know about conservative forces, there's one thing in the definition when we mark the definitions at the end of the year. Time and again you get 0 for this. Because you remember things like dependent of the path and independent of the path. What is the word in that definition that you forget to write? The work done. The work done. Just highlight that because that's the word you forget. Right, so if something is a conservative force, it means that the work done by that force is independent of the path. So it doesn't matter which path you follow. And that is very nice for us to have. What is our examples of a conservative force? A conservative force, gravity, right? Gravitational force. And that is very important when we do things about work, energy, and power. So what I can do is I can ask you, I've got this inclined plane. I'm moving something that is 3 meters. That is point A, that is point B. If I ask you to move something there, I tell you it's a 10-kilogram box or whatever, I can ask you, what is the work done by gravity? How are you going to work that out? You're going to say it's the gravitational force times delta x times cos theta. Just have to give you an angle here, say 40 degrees. You can do that. We've done that now, right? But what are you going to do if I tell you, work out the work done by gravity when I move the box like this? Calculate the work done by gravity when I move the box like this. Is it a problem? Gee, if I have to work out every single little bit, that would have been a problem, right? But what do we know about gravity? Gravity is a conservative force. And what does that mean? It means that the work done moving it straight from A to B will be the same as the work done moving it all the way like that. Or if I chose, I could have moved it like that. Make that root C. Root A, root B, root C. It doesn't matter how I move it because it is independent of the path. Right. So if they in the exam ask you to calculate the work done by gravity for moving like that, you just say, I know about gravity. Gravity is a conservative force. So the work done by gravity will be the same. It doesn't matter which route you take. So I'm not going to try that. I know I can work straight because this is the one that I can do. Is that right? So what does it mean if a force is conservative? It means, most important word is, the work done by that force does not depend on the route that is followed, right? The work done by the force in moving an object between 2 points is independent of the path. So you can move it wherever, right? And then obviously the other way around. If it's non-conservative, then every single path will have a different work done. So just to use that, if you turn to the next page, down there at the bottom on page 12, I'm now going to show you 3 different methods that the teachers and the textbooks use to work out the work done by gravity. Now, if I told you there's a 10 kilogram toy car, 10 kilogram toy car, pulled 3 meters up an inclined plane. The plane is at an angle, this is very small, of 30 degrees there, and they tell you that the height is 1.5 meters. Right. The method that we prefer to use is the one in the definition. Right. So one in the definition, use the whole force. So it's 10 times 9,8 to get the whole gravity. Times 3 times cos, it's moving up the plane, and if it's moving up the plane, it's 90 plus the bottom angle. Right, and then you get minus 147 joule. Right, that's what I prefer you to do. Right, but what you can do is instead of working with only gravity, you can go and split up gravity into its two components. And some teachers like to do that, right? Okay, but it's not necessary. This is actually the way that the definition wants you to do it. But if you did that, then you would have said the work done by gravity is actually the work done by the parallel component and the work done by the perpendicular component. So you are working with them separately. And then if you work out the work done by parallel, it's the parallel component, delta x, and then what would be the angle? It would be the angle between the parallel component. I don't like this because you write down 2 thetas and they've got different values. Right. So I would prefer never to do this. But if your teacher does this, just know where it comes from. She's working with the 2 components separately. But you will get the same answer if you work with them separately and if you work with the single one, which is neater actually. Right, but now we've worked with conservative forces and now we've got a third method. And the third method is the fact that it's conservative. So you can work with the movement that we are asking you, that is root A, or you could have done using a separate second root, root B. So the work done by root A, by working with gravity, root A will be the same done by gravity when you go root B. So now you've got 2 different parts. Now tell me, for this part where you're working horizontal, what is the angle between gravity and the movement? Cos 90. And what do you know about cos 90? 0. So this part of the movement gets no work done. The work done by gravity to move it like this is 0. I know your teachers always tell you, if you are carrying your suitcase at school, your bookcase, how much energy are you giving to your bookcase? 0. Because the force that you are exerting is upwards, but the movement is forwards, right? So you're not adding energy to your bookcase. You may become tired, okay? It's just from keeping yourself up, right? From keep exerting that force, but you're not actually giving energy to the bookcase. Right, so that part of the movement has a 0 work done. So you can actually just go and work out the work done by that. And for that one, it will be gravity delta x cos theta. Now gravity is the whole gravity. What is now my delta x? It's actually the height, right? So now delta x is that delta x, which is the height. And then cos, and now we have to think, for this part of the movement, gravity is down and the movement is up. So you're working with 180. Right. So sometimes they use that one. Everyone happy? So you now see where your textbook or your teacher come from. And they all fit together. And they give the same answer. It doesn't matter. It gives the same answer. So work with what is comfortable, but this is the one according to the definition. Right. Now, back to our first page. Page 10. We've talked about conservative forces. Right. Now, we are going to have a new form of the work done by the net force. We have our work energy principle, which says the net work is equal to the change in kinetic energy. That was up there, right? Now, sometimes we have a problem. Now, just look on the right-hand side on that page. This page 11 is where we did that inclined plane. Is it right? Now, on the inclined plane, the bottom angle was 30. Did we need that 30 when we worked out the work done by the applied force? No. The angle was 0. Applied force, it didn't matter what the bottom angle was. How about frictional force? Did we use the 30 when we worked out frictional force? No. Did we use the 30 when we worked out gravity? Yes. So it would have been a problem if I didn't have the bottom angle, right? For gravity, work done by gravity, you need the bottom angle. How about the normal force? No. So gravity is the only one that needs the bottom angle. And now, if you look on the right-hand side, if you don't have the corner, if there is no corner, right, it will be easier not to work with gravity, right? Gravity is my conservative force. So I work with all the rest. What do we call all the rest? The non-conservative forces, right? So the non-conservative forces is all the separate ones except the one done by gravity. So if there's a work for the non-conservative forces, you add all the work except the one by gravity. And that is the nice to use when the angle at the bottom corner, the angle there at the bottom, is not given, right? When you've got no corner, no angle down there, right? Use this one instead of the W net one, right? Because then you don't need it. Right, then we're back at grade 10. And now I know your teachers in school, they are very pressed for time, and it's not their fault. Your syllabus are very full, right? So they just get to this part and they say, oh, and you've done it in grade 10. Flip the page and go on, hey? Or your textbooks, they do just one example and then they go on, right? You have to be able to do this. And this is actually the easier way to do some of the questions. So let's just look at this. Mechanical energy. Mechanical energy, it's both the kinetic and the potential together, right? And then you get kinetic, right, due to movement, half mv squared, and you get gravitational, EP, mgh. Do you remember them? I hope it's coming back. Right. What's important over there is both G and the V over there has got no sign. No positive, no negative, right? Because energy is just positive. So here, don't put a negative into your velocity value, right? For velocity and gravity here, you don't have to work with positives and negatives. Right, then we get to the principle of conservation of mechanical energy. Now we said gravity is a conservative force. What does it conserve? It actually conserves mechanical energy. So if gravity is your only force, then the mechanical energy at the start and the mechanical energy at the end will be the same. There's no change in mechanical energy, right? So then the total mechanical energy, which is EP plus EK before, is same as the total mechanical energy afterwards, both added together. And then you just have to put it in there. So this is very easy to use. Where can I use it? When you get projectile motion, it's only gravity. This is an alternative way to do it, and it's actually easier. Because with projectile motion, you have to decide, is G now positive or negative? The delta Y is difficult because it's got a direction. But you can do this. It will get the same answer, right? Just remember, they can force you to use a specific way of doing. If they say use principle of conservation of mechanical energy, you may not use equations of motion. Then you're stuck with this. So you have to have all the methods. They can force you onto a single one. Right. So we'll do an example when we get to the questions that we're going to do. I just quickly want to look at the last part, and this is back to grade 12. And that is power. Power. Now, you learned about power in grade 11 for the first time. You learned about power when we were doing electricity. Do you remember electricity? We did power, and we said the power is the work done per unit time. So then we said if you had a light bulb and your light bulb was typically 30 watts. Now remember, we measure that in watts, the power. If it was 30 watts, then it was 30 joules of light energy produced in every single second. So if I had to choose between a 30 watt and a 35 watt, and it's my study area where I need a lot of light, I go for the bigger power, more watts, 35 watts, instead of 30 maybe, right? But it also depends on how effective it is, right? But we're now using LEDs. We're not using any more old-fashioned style bulbs usually, because they had a lot of the energy was heat. And we actually didn't want the heat. We wanted light. So we're now using LEDs. But still, if it's marked 30 watt, it means it's converting 30 watts of electrical energy to light energy every single second. Right. Now we get to work. So what is power in this context? Now, if someone's got a power of 200 watts, it means it's doing 200 joules, it's giving 200 joules of energy to the system per second. And that is just the important thing. It's in every second. And there's another equation. So this one is old news. What is new is that one. You can also work out the work done, or the average work done rather, by the force, right, and it should be a constant force, times the average velocity. Right, how do you get average? You add the beginning and the final and divide by 2, right, to get the average. So let's try and do this. Go back to the problem we're working on page 13. Right, so now on this page we've started out with all the forces working on my washing machine. I've worked out the work done, the net work. I've worked out how fast it is traveling at the top. And now I want you to calculate the average power that the man is doing. Right, the man is pulling up. How many joules per second? What is the power he's exerting? Right, or dissipating. Right, now let's look at the first one. Calculate the average power of the man with that. So, just because I know where we're heading, draw a little line and do it on 2 sides. We're looking at that one. Right, now, the power, what power? Is the power of the man. So which work done is done by the man? The man is the one exerting the force, right? The applied force. So the work done by the man is that 6,000 up there. That is what the man did. The man did 6,000. And now we get to the time. Did they give you the time? No. But if you go back to the question, what do we have? We have that they told us it came out of rest. So we had an initial velocity of 0. We also have a final velocity of 14,14. And we also have delta x. It's moved 3 meters. So what does that remind you of? Equations of motion. So now you're supposed to go to your red information sheet to see if there's a way that we can get delta t from there. So if you look at this one, we don't have acceleration. Don't go working it out. It's not necessary. You can just go and find this equation where you have the initial and the final and the delta x. We've got all those. And then we just work out delta t. So we're starting off. Delta x is equal to v initial plus v final divided by 2 times delta t. Substitute. Delta x was 3, initial velocity 0, final velocity 14,14 divided by 2, and I'm looking for delta t. So if you work out delta t, all right, 0,424 seconds, or more or less, and then we're going to use it in this occasion. Right, depending on how many digits you leave in your calculator, you might end up with 14150,94 or 14140, right? It doesn't matter, they mark the whole range. So you can leave that number in your calculator with all the digits. So they will mark anything from there to there and anything in between. Right. Everyone happy? So this is one way to calculate the power. Now let's do the same thing with the second method on the right-hand side. Calculate the average power of the man with P average equals F times V average. Now we're working with the man, so which force do we need? We need the applied force of 2,000. And how do I get the average velocity? That will just be the initial plus the final divided by 2. That gives you the average velocity. And then you once again end up with 14140 watts. So both methods gave you same answer. It's nice to know, so it doesn't matter which one you use.